Good evening, students. Am I audible?
Yes, sir.
Thank you, Jitendra. On behalf of IGNO Regional Center Bhubaneswar, I welcome you all to this online platform of classes, your theoretical classes of your MCH-02 paper of PGDSC program. So, up to yesterday, we have completed or we have covered up your unit 6, that is block 3, I think. And today we will discuss the next block, that is your next block, which is about your unit 7, that is gas chromatography. So as already we discussed, this chromatography method is all about the separation technique. And in our previous classes from unit 1 to 6, we have discussed the different separation techniques with our solvent extraction part 1, part 2, followed by the planar chromatography, which is your paper chromatography or thin layer chromatography. So in paper chromatography, we have two types, that is your ascending paper chromatography or descending paper chromatography, which is your two-dimensional chromatography. So in thin layer chromatography, we have a thin layer chromatogram in which some slurry is prepared by using silica gel particles with different mesh sites, and that slurry is spread uniformly on that your thin layer plate, and this is acts as the stationary plates on which a selected solvent is run, and the sample gets split, or the different components get separated from the sample according to their interaction with the stationary phase, and whether it is paper chromatography or thin layer chromatography, your mechanism is your absorption mechanism, in which the thin layer of the paper, it acts as the uh, your adsorbent, and the constituent particles which are get separated from the sample are acts as the adsorbate molecules. So in gas chromatography, let's have one PDF that is available with me. This one, and your chromatography, this is covered, and we have the application in column chromatography, and this is your India PLC. This is the PLC plate where different spots are obtained after putting the PLC in the suitable solvent, and this is the gas chromatography we have. So this gas chromatography was discovered by Martin and James in 1952, and this is a very popular chromatographic method in which the components get separated using either solid stationary phase or liquid stationary phase. And here gas is always treated as, or it is applied as the mobile phase in this chromatography. So according to the solid phase used, the gas chromatography is primarily divided into two types, that is gas solid chromatography and gas liquid chromatography. So in gas solid chromatography, we have the solid as the stationary phase, generally carbon or calcium silicates or polymers, which are used as the stationary phase for GSC. And in GLC, gas liquid chromatography, generally the liquid maybe the water or any suitable solvent, it is used as the mobile phase. Sorry, it is used as the stationary phase in GLs, gas liquid chromatography. So this technique in which the technique in which volatile components of mixture are separated by partitioning. Yes, it is the mechanism here. It is partitioning. Now here the partition coefficient is calculated or distribution coefficient is calculated. So by partitioning between stationary solid or liquid phase and mobile phase gaseous phase. So here the mobile phase, that is the gas, which is known as the carrier gas tank, it should be chemically inert, having high coefficient of thermal conductivity, and it must be dry and pure. So pressure regulating valve maintain pressure. So the carrier gas which is used as the mobile phase may be helium, nitrogen, hydrogen, carbon dioxide, etc. Then the second one is the sample injector. So it is a part of the chromatography which is used to inject the sample from which the components are to be separated. So important to introduce sample in short time and in smallest volume, injected directly into column through inlet for high boiling solvent to one heated injection chamber. Sample is vaporized and vapors are swept by carrier gas into column. So first what happens, a sample gets injected inside the gas chromatography and followed by your high temperature is applied by which your sample gets vaporized and the vapors are now moved towards the column. So this is the mechanism of your, yes, this one. So just see here. So this is the injector, that's the point in which your sample gets injected, and this is your syringe in which your sample gets filled and it is injected into this sampler or sample chamber. Then we have a carrier gas, maybe hydrogen, helium, nitrogen, etc. These gases, helium, nitrogen, hydrogen, or carbon dioxide. This gas will have some regulator, and this gas will pass through this channel and it is injected through this injector where sample is already there, and this gas and with some filaments which produces heat, and the sample is now vaporized to vapor state, and these sample vapors were injected into the column after the, and the sample is now accelerated through the column, and after the acceleration through the column, the sample or the different particles gets detected with the help of this detector. So this is a very simple phenomenon where just remember a carrier gas cylinder is used which generates the pressure, and this chamber which is a oven, that is temperature is high, in which the sample is converted to vapor state, and the sample vapors are injected or passed through this column, and so pass through this column by which different components get separated on the basis of their interaction with the stationary phase. So this is the stationary phase we have. So if this stationary phase is a solid, then this is called as the gas solid chromatography. If this is a liquid, it is known as the gas liquid chromatography. In both the chromatography, the mechanism is a partition mechanism. So this is another, so this is another form of your gas chromatography in which helium is the carrier gas. There is a regulator here, This is the injection chamber in which sample is gets injected, and this carrier gas and will create the pressure and a neutral environment. And this is inside the oven or thermostat chamber. The sample gets vaporized, and the vapor of the sample is allowed to pass through this column. And after the passing of this column by the sample, what happened? Different components get separated on the basis of their partition coefficient or distribution coefficient, and accordingly, different components gets detected with this detector. Okay, and after detection, we got a chromatogram like this, and your partition coefficient, distribution coefficient calculated accordingly. So this is a very simple and very effective mechanism of your gas chromatography. So the column used. So this is the column. This one. This is the column. So this column is made up of glass or metallic tube, which is copper, aluminum, or stainless steel. It is U or W bent, placed into oven. So it is a U shape or W bent shape, which is placed in the oven. So number one is packed column. It is tubing 0.5 centimeter diameter, 1 to 20 centimeter long. It has uniform size. It is inert. Thermostat is there. Solid support. It is diatomaceous earth Teflon powder or a glass beds coated with liquid film. So this is the packed column we have, and if the column is open, then open tubular also column is used in gas chromatography. It is a tubing of diameter 0.2 to 1.2 millimeter, 30 to 100 meter long. For high resolution, tubing may be 12 kilometer long. Columns held at predetermined high temperature. So this is the primary construction of the column, which may be called as the stationary phase of gas chromatography. And the third one is the detector. The detector is to record the separation, and it shows the result on a monitor. So detector, it is thermal conductivity detector, argon ionization detector, and flame ionization detector. When carrier gas enters to detector, electrical signal is generated in proportion to concentration of substance. So when the vaporized sample is allowed to pass through that column or the stationary phase, in detector, some electrical signals were obtained depending on the concentration of the substance that gets separated from the sample. So these signals are recorded. So this is a very sophisticated gas chromatography instrument in which your carrier gas cylinder was outside, and that the regulator pipe will be attached to this gas chromatography machine. And if you put your sample here, this is the sampler or sample chamber. With the help of a series, you put your sample and just on the sample on the machine. Sorry, on the machine. And what happened? The thermostat will activate it, and your sample gets converted at vapor state. And after that, vapors of the sample is allowed to pass through this column, and depending on the different your separation state, the detector gets different electrical signals, and that signals are now converted into a chromatogram, which is displayed on this monitor. Okay, this is about gas chromatography. Doing a thermal conductivity detector, this one, there is no point to discuss all these things in detail because this is not needed. Then we have the application. So this is applicable to biofuels, biogas analysis, analysis of auto exhaust gas, identification of natural products to process control, then biomedical application, analysis of body fluid, organic analysis, carbon and hydrogen can be determined by burning sample in dry steam of oxygen. Then application is separation of benzene and cyclohexane. GLC used to study reaction mechanism. GSC used to separate gases which are hydrogen, oxygen, carbon dioxide, CH4, methane, and your acetylene, etc. So this is a chromatogram we have in which 10 components get separated with time. So this is a typical gas chromatogram in which your one is your hydrogen. This is the for your hydrogen, which is separated first. That's why it is mirrored to zero. Then carbon dioxide, ethylene, ethane, acetylene, then disregarded oxygen, that is number 6. Sorry, number 5 is acetylene, then number 7 is your oxygen, 8 is nitrogen, 9 is carbon monoxide, and 10 is methane. So this is disregarded some substances there. Then what is the advantages of gas chromatography? So this is extraordinarily sensitive method because as the vapor state of the substance or the mixture which is under investigation, from the vapor state we will get a very correct report of that sample of separation. So many samples can be detected in small quantity like 10 to minus 15 kg. Separation achieved in less than a minute. Volatile compound can be separated. Give satisfactory separation even of complex mixtures. Simple technique can be used as routine lab practice. Can be used as preparative method by using non-destructive detectors and condensing the vapors emerging from collection. So, so for BSc students or your diploma students, what are different job opportunities after your this course? You may pursue your jobs like UPSC, master degree, integrated PhD, MBA or MCA, and then followed by your MSc. And if you crack the industry, you have the industrial part with the quality assurance, quality control, or research and development. It is or research associate or project associate you may join. Or if you are able to crack the national eligibility test or state eligibility test or aptitude test in engineering GATE, you may pursue your PhD. It's a doctoral degree. So after that, you may go to industry, scientist, or educational field. So this is the MBA MC. I don't go to that part. Important branches of chemistry for MSc students: organic, physical, inorganic, industrial, analytical, polymer, drug, medicine. Then agriculture and paramedical, I think, biomedical, biochemistry, environmental chemistry, astrochemistry, business chemistry, or nanoscience. So this is the basic career perspectives of your BSc chemistry or PG BSc chemistry. So this is all about the gas chromatography we have. Or these are the, in gas chromatography. Just remember there is a carrier gas which is used to create the pressure inside your your thermo oven, or it is a thermo chamber we have. Then the sample is converted to vapor state, and the vapor of the sample are allowed to pass through the chromatogram made up of copper, aluminum, or stainless steel. After passing through the chromatogram, after passing through that, yes, your chromatogram, your different components gets detected depending on their partition coefficient, and they are producing some electrical signal at the detector point, and that signals are converted to some graphs which are known as chromatogram, and in the monitor you will see the graph or chromatogram we have. Then some equation. This is the flow rate of carrier gas, Dr equal to Pr into Fc, where Dr is the retention volume, Fc is the, and Pr is the peak maximum. So just go through these things. Okay, so this is the retention time versus the detector response, and this is for sample AC, and it is the chromatogram standard solution of ABC. This is just an example, and different examples are there. That is storm dead volume is Tr gas equal to Tr minus T naught, where Tr is the adjusted retention time and T naught is the retention time of air peak. Then we have the Vr gas equal to Vr minus Vm, where Vr is the adjusted retention volume, Vm is the hold up volume, and Vr is the adjusted retention volume for solute A, B, and C. So this is just an example. Then we have the column frequency and the separation factor. So the column frequency, it is about the efficiency of your column to uh, partitioning or to separate the different components of a mixture using the separator factor, or we may say it is a partitioning factor or distribution factor. So the interaction and which determines the relative position of solute peaks on the chromatogram. The separation factors of relative retention is expressed as the ratio of retention time. Thus, alpha is determined by the respective distribution constants Kc of the solute in the liquid phase at a given temperature. The idea of increased column and solvent efficiency is illustrated below. So what is column efficiency? It is measured by the plate number n. To compare column efficiency, it is the plate number. Just see here. So this is the plate number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So how much number of plates are there? So this is one of the big factor of your column efficiency. To compare column efficiency, one must specify the liquid stationary phase, solute, temperature, flow rate of carrier gas, and sample size. The plate concept is carried over from distillation process, where historically the past efficient column were in fact composed of distinct plates. In the lab, however, the packed distillation columns are most commonly employed, and the plate number is theoretically concept introduced so that column performance can be evaluated. So this is a peak we have got from a chromatogram, and here each and every point is measured, and this is your if a tangent is drawn, then what happen, we will get the number of plate equal to Pr by sigma square, which is equal to the equation for this curve or for this peak. It is tends to be 16 Pr by Wb square equal to 5.54 Pr by Wb square. So this is a plate height we have. So W into H equal to L by N, where L is the column height, H is the unit of the length, and for greater than n for comparing efficiency of columns of different lengths. And we have the height equivalent to one theoretical plate, which is known as HCTP. Height equivalent to theoretical plates, and which is carried over from distillation technology. A good column will have a large L and small x. This is very important. If you have a good column, then the column should have a large number of plates, and the height must be small, because if the height is small, then the sample gets rotated or gets passed over that column very rapidly and smoothly. This is another measurement, that is resolution of column, and this is the respective equation we have. We just go through this. Then we have your uh, that equation is now reduced to R is equal to D by WB, where your D is the distance between two consecutive peaks, and WA is the distance between your lower part. That the tangent is drawn and the distance is now measured. The three principal contribution to the broadening of band, yes, that's the broadening of band. These are multiple path effect, or EBD diffusion, which is denoted as A term, molecular diffusion, that is B term, and resistance to mass transfer, which is termed as the C term. So the height of the plate, it is equal to A plus B by U plus C by Cu, where U is the linear velocity. Okay, so there are different terms, that is path effect, molecular diffusion, or resistance to mass transfer. So U is the linear velocity, which is the length of the column divided by retention time of the air in second. Then we have the HCTP equation of this one. Let's try to figure out this equation and try to remember all the parameters. So in this equation, lambda is the parameter, which is the measure of cracking irregularities, and your dp is the diameter of cracking the particles. Gamma is the correction factor accounting for the tortuosity of the gas channel in the column. EF is the effective film thickness, a measure of liquid loading of packing materials, followed by your D liquid diffusion coefficient of the solute in the liquid phase, D gas, that is the diffusion of the solute in gaseous phase, U is the linear gas velocity, and K dash is the capacity factor, which is equal to F liquid by F gas. Then this separation technique depends on the particle diameter of the column, and it will be 100 to 120 mesh range. And flow rate also, it depends, whether the height is small, the flow rate will be more. So flow rate also determines the separation of components. Then the carrier gas which is used, whether it is free from impurity or not, and pure carrier gases of lower molecular weight are generally generally preferred for this separation technique, and generally helium or hydrogen gas is used. And the liquid phase, which is used as the stationary phase for this chromatography, that is gas liquid chromatography. The liquid must have low viscosity, must have low vapor pressure, with good absolute solubility for the sample. It is very important, because the liquid must have the solubility factor, a good solubility factor, and we have the amount of liquid phase, that the low liquid loading, that is 1% to 10%, have the advantages of fast analysis and lower temperature operation. Low liquid loading, however, reduces the sample capacity and may require a highly inactive solid supports. So in this, then the pressure which is created by the your carrier gas, that may be helium or your hydrogen. So a majority of practical gas chromatographers work at an outlet pressure of 1 atmosphere so that operation at optimum flow rate fixes the inlet pressure. However, best efficiency is obtained at low inlet out pressure ratio. Then the temperature which is maintained to, and it is responsible to convert your sample into vapors, or it changes your sample into vapor state. So after the conversion, your vapors of the sample gets passed through that column with different interactions. That may be your partition, and the accordingly your partition coefficient or distribution coefficient is calculated. So column diameter, capillary and evaporative column experiments indicate that efficiency is improved with decreasing internal diameter. Then the solvent efficiency, which is the mobile phase and different interactions, that is four interactive forces which can aid in the this separation. These are orientation, known as Kisson force, induced dipole divide force, dispersion or London force, and specific interaction forces. So in your Kisson force, you have the interaction between two permanent dipoles, maybe positive pole and negative pole. So automatically they have some interaction, and here hydrogen bonding also plays an important role. But in Debye forces, what happened? Induced dipole is there. That means there is a molecule with permanent dipole moment and a molecule with no dipole moment. So the permanent dipole moment, when it's placed in the vicinity of a molecule with no dipole moment, then in presence of the permanent dipole moment, an induced dipole moment is and dipole moment is induced or created within the non-polar molecule. So this is known as induced dipole. Then we have a dispersion London force, that is between non-polar. So when two non-polar substances are come close to each other, so due to their different charges or ions present in that substance, then weak intrapolar, that is dipolar interaction is created. In specific interaction, we have forces resulting from chemical bonding, complex formation between solute and solvent, the interaction determines the solubility, and so on. So it is the distribution constant Kc, amount of solute per unit volume of liquid phase divided by amount of solute per unit volume of gas phase. So it is the stationary phase is GLC, and it is the mobile phase is GLC. As we know, in the numerator we have the stationary phase, and in the denominator we have the gas phase. So accordingly, the calculation is made. This is your distribution coefficient or partition coefficient. The solvent efficiency and temperature we have. So as we know, the solvent efficiency and the temperature inside the oven, both are dependent on each other. So when solvent efficiency, it is let us we have the distance covered, that is x1 by x2 dash by x1 dash is k2 by k1. So we have the separation factor, that is equal to x2 by x1. Just here two components are there. This is the air we have, and the distance covered will be x1, and the distance covered by the component 2 is x2, and the volume uncorrected, that this is the total volume. This is your x2 and x1. This is actually bar, x2 gas and x1 gas. The number of plate, the same, that is the N, it is equal to 16 R square, and so on. So, and this is your example how your different components get separated after different time intervals. And the separation shown below was obtained within a 3-meter column. the minimum column length necessary to obtain integration of 1.5. So here the number of plates is calculated. That is your 17 by 1. That is x is 17 and y is 1. Then the number of plate is 4624 plates. Then if we calculate the alpha, then this will be the 1.231 and K2. Then accordingly the calculation was made, and lastly we have the 0.75 meter of your required length of the column. And this is the instrumentation which is already discussed, that there is a carrier gas chamber, there is a regulator, and we have a sample injector or injector chamber, in which with the help of a syringe we put the sample inside this chamber, and after that this sample gets converted to its vapor state, and the vapor of the sample is now passed through this channel and this column with different plate numbers, and after that the different components get separated, and they put electrical signal in this detector, and after that signal the chromatogram was recorded. Okay. So the mobile phase, the carrier gas, which may be inert, dry and virtually pure impurities. This is already discussed. And detector, a thermal flame ionization and electron capture detector. So for thermal conductivity, it is helium carrier gas. For flame, it is helium or nitrogen. For electron capture, it is very dry nitrogen or argon 5%. So flow controller was there, pressure regulator was there, everything is there in the sophisticated gas chromatography. And this is the effect of increasing flow rate. When the rate increases, how the chromatogram gets changed, that is highlighted. And this is the column we have. This is the column in which the vapor of the sample is allowed to pass through, and accordingly your different particles gets interacted, or the partitioning coefficient, the distribution coefficient, the particles get separated. And this is the liquid phase, that is the uh, your known as the open tubular column, in which the liquid gets spread over the column like your thin layer chromatography, and we may treat it as the stationary phase. So these are some sorry. So these are some capillary action with the packed column we have, and accordingly your tabulation was process separation. And this is how the separation is done. This is the zero time. After 1 minute, the partitioning was carried out, and after 2 minutes, the particles or the constituents get separated. And these are the stationary phase support of liquid phases or liquid phases, supersymmetric liquid phases, liquid phase percentage, effect of column temperature, Kodak pack as packing material. Stationary support we have. This is already discussed. What is the area? What is the port structure? These are already discussed in our PowerPoint presentation with different news sites. And this is the chemical analysis support. We have the silicon oxide, the fire break. It is C22 it is the commercial name. Selite number is 535. This is chromosome P and chromosome W. So chromosome W, it is a flux calcined diatomate support. It is similar in performance and property of Selite 535. So these are all commercially available your stationary pages. So the liquid page, then it is your It should be good. It should be a good absolute solvent for sample or solute. If solute are sparingly soluble in the liquid phase, they will elute rapidly and separation will be poor. It should exhibit difference in solubilities for different solutes in the sample. It should have low vapor pressure, like 0.01 to 0.1 millimeter at operating temperature for a reasonable column life. It should be thermally stable. It should be chemically inert towards solute of interest at the column temperature. And this is some compounds which they have with different seasonalities. Okay, and these are the commercial names of the seasonalities used for preparation of these samples. The big table is there. The super selective liquid phase we have, then the alkene which is separated by using the silver ion, that is the silver nitrate. And the tetracyanoethylated pentaerythritol (TCP) is also highly selective for aromatic compounds. So this is the aromatic compound we have, and accordingly, your this TCPE. This is also very important liquid phase for separation of aromatic compound. So liquid phase percentage, this is also a factor for this analysis, that 30% liquid will use at 50 degrees centigrade. We have the chromatogram light mist, and the percentage is decreased and temperature remains same. Now it is more or less prominent peak, and if your 10% liquid phase is there, then accordingly it is again switched off, and when your liquid phase is gradually decreased to 1%, at the same temperature we have a peak like this. So column temperature we have, similarly how the column temperature 30 degree to 40 degree and 40 degree to 50, 50 to 60, it impacts the chromatogram. It is highlighted here. In Corapic is a porous polymer composed of ethyl vinyl benzene cross-linked with divinyl benzene to form a uniform structure of a discrete four-side. Corapac column contain only the porous polymer beads screened to a definite ness. So then the detector we have, it should be adequate in selectivity, sensitivity and detectability, linear response to solute that extends over several order of magnitude. Operating should be operating in a temperature range from room temperature to at least 400 degrees centigrade. High reliability and ease of use. A short response time that is independent of flow rate. Similarity in response towards all solutes. Non-destructive for solutes. Noise and minimum detectable quantity. So these are some characteristics of a good detector used in gas chromatography. This is the detector response versus the integral chromatogram, and these are some equations we have. Let's try to read out all these equations. Then we have the yes, we have the detector, that is thermal conductivity detector TCD, flame ionization detector FET. So this should be FID. Okay. So flame ionization detector or thermal conductivity. So for different detectors we have, this is FID, this is flame ionization detector, and we have TCD also. So detector sensitivity, detector response, is noise and minimum detectable limit. So these are all some electrical signals that is came from the different components which were supplied from the sample. And linear detector range we have thermal conductivity detector TCD, flame ionization detector FID, thermal application is there, which is also known as a catharometer. That is also known as the TCD, thermal conductivity detector, in which the thermal application is there. And flame ionization, a flame is used, which is used to ionize the sample, and accordingly the detector detects the different components, and these are some gases which are used as components giving little or no response in FID. So these gases do not respond to FID detector. Then we have the ECD, electron capture detector. This should be specific, selective of to halogen, and sensitive to a few parts of brilliance. Then go through this thing, what are the different isotopes, the characteristics, and their response towards ECD. In a helium, HID, helium ionization detector. This is a universal detector, photoionization, and it is sensitive to functional parts per million. Then at the end we have the flame emission detector, which is also known as the alkali flame detector. And as it is the alkali flame, it is written alkali means it is a type of base. And the flame emission detector, it consists of a normal flame detector plus the addition of a small alkali salt. Here it is given alkali salt pellets, maybe sodium hydroxide, and accordingly the detection was made. So this is the alkali flame detector. So in which all the constructions are same, only the detector is different. Okay, it is the sample injection chamber, and it is the carrier gas we have. It is the it is the thermogram we have, or oven we have, in which the sample gets converted to the vapor state, and after the vapor of the sample gets passed through this column, then only the detector role was started. Okay. So sampling and introduction, sample into the chamber. So there should not be any hazard in sampling. Introduction of sample to this chamber, sample site, injection system, sample injection port. These are very important factors. Then we have, this is the syringe which is used to inject the sample inside the injection chamber. Then we have the carrier gas we have. Then accordingly, other different applications to identify the compound qualitatively, and quantitative estimation was also there, and some examples of the applications from here. So the identification, how what type of compounds gets identified qualitatively and quantitatively, and this is all about your gas chromatography. We have the environmental analysis, so water analysis, air analysis, chemical and toxicological logical analysis, and forensic science also apply or use this gas chromatography method to separate the blood sample, separate the urine sample, or some crime investigations. We use this to see. So this is all about the gas chromatography, and in the next unit we will discuss the HPLC, high performance liquid chromatography. So here I am taking a 5 minute break, and after that we will meet again. So till then, keep patient students. So thank you, students, for your pac- patience stay. So now the next unit it is all about your high performance liquid chromatography. As we already know that in liquid chromatography, if your stationary phase is solid, then it is named as liquid solid chromatography, and the stationary phase is liquid, it is known as the liquid liquid chromatography. So in liquid solid chromatography, the mechanism involved is for separation, it is your adsorption. For liquid liquid chromatography, where the stationary phase is another liquid, the phenomenon, the mechanism involved is a partition. So under LSC, that is liquid solid chromatography, we we calculate the retention factor, and under your LLC, liquid liquid chromatography, we calculate the partition coefficient or the distribution coefficient. Okay, just wait one call. So in high performance liquid chromatography, this is a very sophisticated, high, this is modern technique, which is very sensitive as well as it takes less time um, than the traditional liquid chromatography instrument. Then under this one, we will discuss, and this was first introduced in USA in 1964, and just go through this paragraph, and we will have the objective principle, and the principle is same. We have the liquid chromatography, in which whether the stationary phase is solid, it will be your liquid solid chromatography. If it is liquid, then it is liquid chromatography. So in LSC we have the adsorption phenomenon, and in LLC we have the partitioning phenomenon. Okay. So these are some particle sizes, uh, particle sizes uh, by which different columns of the SPLC is selected, and when your modified. So if it is particle size is less than 1.150 micrometer, then your column diameter is this, and accordingly when the size reduces, your column diameter also reduces. Then similarly the length of the column as well as number of plates which are used in our high performance liquid chromatography, it is the equations we have, where it is the velocity and distribution coefficient dn in the mobile phase, and ds is the mobile distribution coefficient in the stationary phase. Then we have the different equations based on your um, length, number, and height. Then the SPLC instrumentation, just see here, this is the instrumentation we have, and here we have two your solvent reservoirs are there, and here the helium is used, and we and here this is the your sample chamber. Okay, so after the solvent, it is proportionating valves is there. So the solvent is now, so this is the connection with the control section to know the solvent concentration or solvent volume inside this reservoir. So when the solvent is now move or pass through this pipeline using this pump, and when the sample is injected, it is now sample is injected, it is now your pass through this scavenger column, that is your column which is used as the stationary phase in HPLC, and accordingly your where the different components gets separated, and this is the analytical column. Again the separated components gets passed through this column, and we have the detector which is accepting the electrical signal, different electrical signals from the different components present in the mixture, and finally the after the detection we have the chromatogram. So this is the flow of your sample from mobile phase to stationary phase, and your stationary phase is of two types here, that is scavenger column, GAD column, and your analytical column. So through these three columns the sample is passed, and based on the interaction your detector detected these different components. Okay, so this is a sample injection system here, this one. So the sample in and sample out, two types of things are there, and this is a mobile phase. So these are the channels which are connected to your HPLC. So inside this is the sample in, and this is the column we have. So sample in column, and the sample is now out. So the column, it is the heart of SPLC, and where actual separation occurs. Separation column in FPLC is usually made up of heavy wall, glass lined metal or Q16 grade stainless steel, which is the high performance grade steel, and its market price is also very high. Different grades are available, that is 304, 204, 316 is the best stainless steel available in the market, and that can withstand high pressure, which is inert to chemical corrosion due to mobile phase. So these things are there, and we have the yes, this is the stainless steel SS. This is the utility material good for high pressure system. We may use the polyether ketone, that is the polyether ketone PEG, and this is the use we have, and tech gel, titanium, all these things are there which can be used as the material for your column. Then the guard column, in order to increase the life of the analytical column, a short guard column, also known as pre-column, is placed. It's placed before the main column, and it removes contamination from the solvent. So guard column serves to saturate the mobile phase with the stationary phase so that leakages of stationary phase in the column are minimized. So this is just a precautionary column before the analytical column we have. In the packaging, we have different commercially available packaging materials are there. So these are generally used, and in silica or silica gel in acidic media or alumina in basic media is generally used, and we have the 3, 5 or 10 micrometer diameter of columns are available, and the supporting material which is also called bonded phase chromatography BPC is also applicable to this HPLC. So these are just the bonding or packing materials we have, silica and alumina. Just try to remember the three materials here. Then this is a solid core, deep pores, then these things are there. Spherically bonded phase, porous, this is the porous one, and porous particles are also there. Then you have macro porous particles, this is a monolayer, dense and short, cross-linked, diluted and long, multi-layer, controlled spacing and bulky, coating, B and C both are your large, this is your biopolymers. So these are various shapes of bonded HPLC column packing material. A is the types of bonded phases, topography of ligands, size of ligands. So this is all about your what type of bonds are made by the part constituents with the stationary phase. This is the type of ligand, and this is your C is your site of ligand. Then you have adsorption chromatography. As we all knew that adsorption, there are two things, adsorbate and adsorbent. So adsorbent is the surface and adsorbate is the particle. So in if the so the stationary phase may be treated as the adsorbent, and the component or the constituents in the particle in the mixture may be treated as the adsorbate. So here it is your silica gel depicting various types of hydroxyl group that interact with a group of solute or solvent. So silica gel forming siloxane bonds or silanol, that is free OH is there, or hydrogen bonding is also happening here. So due to these different type of interactions, the your components gets attached to the solid surface. So the the different activity that increase in the order, that is bound, free, and hydrogen bond. So after that is a partition chromatography, in which we have the liquid chromatography, where liquid is acts as the mobile phase and another liquid acts as the stationary phase. And here the partition or distribution coefficient is measured. And here the this is your silicone or siloxane. Uh, this is forming a cross chain or cross link silicones. This is silicones, cross-linked silicones. This is organofluorosilane. These are made up of, and this is your trimethyl silanol reacts with your trialkyl. Uh, this is silane chloride forming this one cross-link. Then after we have the sample, column packing and mobile phase. So if the sample is low, moderate polarity, then it is up to carbon number 18, that is very long. And the mobile phase will be methanol or water, that is polar. And if it is moderately polar, then it may be extended to carbon chain of 8, and it is acetonitrile or water. If it is highly polar, then it will be 1,4 dioxane or water, and it is applicable to two carbons. Ion exchange chromatography, where two types of ions, positive and negative ion, gets exchanged, and we have the chromatogram. And this is just the ion exchange field. We have inner pore, active capacity, macropores. Just try to remember one to two examples. Then we have the reaction, that is an alkene reacts with an aromatic compound to give an adduct or the addition product in presence of silica. And here also one your aromatic alkane reacts with your um, ether, chloroether, to give the product. Here we have the weak anion exchanger, and this is a strong anion exchanger we have. In size exclusion chromatography, this excluded the higher sized particles from the lower sized particles. So this is size exclusion. So the smaller particles gets separated first, followed by the larger ones. Here the dimension of the particle size is there, operating range is there. So according to the pH, the different particles get separated. That is the type, particle size, average score, and molecular weight exclusion limit. In ion chromatography, the same. We have the ion, and when it is the sample is injected, it is passed through the column, and accordingly, this is the element or solvent reservoir. This is the pump. Sample is injected. It is passed through this column. It is a detector, followed by the or suppressor, where the ions gets generated, and the conductivity cell is detect the formation of anion or formation of ions, and according to the electrical signal, the detector detects the different components. The chiral chromatography, in which a chiral carbon is there. A chiral carbon is a carbon which is bonded to four different groups. This is based on your stereochemistry. So a chiral center is there, which is used as a prime factor for the separation. So here just see this copper is set to the chiral center because it is bonded to four different groups. That is copper linked with oxygen, and this nitrogen, this oxygen are here. Just group is separate, and here this is separate, and here also it is separate. And this copper is the chiral copper. Okay. So an atom which is bonded to four different groups is said to be chiral center. Also, some might pronounce it as the chiral. So both pronunciation is correct. You may uh, pronounce it as chiral or chiral. Then the chiral centers, when it is used, it is known as chiral chromatography. The amino acid choline, it is also a chiral center, and the copper ion gets attached to it. The packaging material for the stationary phase, and this is the absorption phenomenon, and what are the applications? This is non-polar to moderately polar. Then this is the packaging bonded phase, and this is moderately polar octyl, that is C8. This is bonded pressure chromatography and your ion partitioning chromatography. Then the things are there, solvent supply system. We have the solvent supply system in terms of a reservoir which is attached to a pump or a regulator regulating key is there which regulates the pressure of your eluent or the solvent, and it should dissolve the sample, it should keep the column stable, it should be compatible with detector, it should be immiscible with the stationary phase, viscosity should not be high, active chloride should be avoided when using the glass column. So all the things, all the characteristics should be a solvent or an eluent should have to act as a good solvent for SPS. Then we have the solvent strain parameter physical property, and this type of table is already discussed in liquid chromatography. And we have the gradient illusion, that is solvent reservoir, we have ABC, and accordingly the depending on the polarity and the application, the solvents are used accordingly. Then the pump, everything is given here in details. What is the pump, what is the pressure created, and what is the flow rate, or everything is given here. So try to read out these things and find out the important sentences or the data you are required for your examination. So reciprocating piston pump, series type displacement pump, constant pressure pump, pneumatic pump. So different pumps are also described. So after that is the detector. In SPLC instrument, and it should be chosen very carefully, as we have different type of detectors like a thermo or differential detector, thermoconductivity detector, ECD, flame ionization detector, FID. Uh, then we have the different detectors we have, and it should have linear response to solute concentration. It should respond to solute only and not to solvent. This is very important. It should be insensitive to change in temperature, pressure, and flow rate. The detector should respond to only solute, that is the component or different uh, element present from a separated from a sample. So bulk property detector, this type of detector measures an overall change in physical property of the mobile phase, and without solute, then solute property detector, it must be small, compatible with liquid flow, it should have good stability and reproducibility, it must have low dead volume to minimize extra column and broadening, it must have high reliability and ease of use, it must have small response time. So after that, there's detector type we have. So it is a detector property, and your linear range, commercial availability, and LOD. LOD will depend on the compound. It is a mass, and we have the optical detector. So the optical detector, it uses the quartz. It has a fixed wavelength, variable wavelength detector, and scanning wavelength detector. Then fixed wavelength detector, where the wavelength gets fixed, like 254, 280, 313, 354, or 365 nanometer. In variable detector, the wavelength gets varied, and we have the schematic diagram of a variable wavelength detector where the wavelength gets varied. and here your source is there. So through a lens, it is now convex, and a mirror is there, and it is another mirror. So here the radiation is grating another mirror, then it is go to the sample. So this is how your detector is operated. Then scanning wavelength detector. Here the wavelength is 190 to 600 nanometer with 0.01 second of time gap. Infrared, where IR radiation is used. Fluorescence, where your singlet to singlet transition is there. It is known as fluorescence. Then differential refractometer. It is another refractive index between the reference and the event. So it is a monitor which shows the difference in effective indexes. So this is the schematic diagram we have. Then your electrochemical detector, where we have the Teflon spacer, working electrode is this one, and mechanized F block is there. So just do it, students. So after this is a mass spectrometric detector. This is a very useful instrument, that is LCMS, which is liquid chromatography mass spectrometry, which is used in the spacecraft GCMS and LCMS. Specifically, GCMS was used, and this LCMS is also very sensitive and well advanced and modern tool to separate or to know the different constituents or components present in a sample. So here the liquid chromatography acts as the separator which separates the components, and mass spectrometry simultaneously determine the mass of the component which is separated from that sample or the mixture. This is a very very useful tool, LCMS and GCMS. And after that, we have comparison of SPLC detector. Just go through these things. Which detector is having some positivity and some negativity, which is having more sensitivity, the less time required for the analysis, etc., etc. So this is the company Agilent. Is a good company from USA. We supply your LCMS, DCMS, HPLC machines, and we have the optimization of separation. Then this is the example of different samples with different solvents or the eluents. What is the advantages? This is very important. This may come in your examination. So this HPLC is a very fast separation method with analysis time as small as less than a minute in some cases. HPLC is a useful separation method with high resolving power and a quantitative analysis method with low detection limit and high accuracy. It is especially useful for resolving optically active compounds, though different types of columns with chiral stationary phase are used. The technique is applicable to small amount of samples where even trace amount of solute may be determined. All kinds of solids soluble in suitable organic solvent and liquid samples can be analyzed, though gases cannot be analyzed. These are the advantages of your SPLC. And SPLC is a wider applicability in pharmaceutical and food processing. It is specifically useful for continuous monitoring of the column effluent, and thus it can be used for any online process. It provides repetitive and reproducible analysis using the same column. HPLC is being widely used for the speciation of ionic and non-ionic species, that is polar and non-polar, such various organic and inorganic form of arsenic. It is more versatile than gas chromatography. It is non-destructive method. It can be used for the separation of close related compounds. It cannot be used for the analysis of volatile compounds, which can be detected by GSC. Sorry, GC, gas chromatography. Sorry, it cannot be used for the analysis of industrial products such as alloy, polymer, etc. High purity solvent are required because any impurity may affect the separation evolution. It requires extensive training in order to operate the instrument and optimize the condition. Sample preparation is often required, dissolution and dilution, etc. So comparison with GC is mainly applicable to volatile substances, where SPLC it is non-volatile. The amount of sample required in GC is very few nanogram, but in SPLC, a fraction of microliter may be sufficient. The column tubing in GC can be circular in a loop or bend, but in HPLC it should have a straight column. It is correct. In GC it is circular or a loop. The instrument setup in two cases is widely different. In GC, it is essential to have a sample injection chamber, whereas in SPLC, it is often high purity solvent is used and generates a pressure gradient, and after that the sample is injected. Though some detectors are common for GC and SPLC like FID and ECD, so SPLC has a wide range of detectors which detects various components. The optimization of experimental procedure in GC is easier, whereas in case of HPLC it is difficult. The basic mechanism of separation in GC is adsorption or partition, but in HPLC it is either adsorption, partition, ion exchange, or side exclusion, etc. GC has limited applicability for gaseous solutes, but in HPLC, the applicability to a variety of organic and inorganic compounds. GC cannot be used for the separation of ionic species, whereas HPLC can. Then we have the application. Just go through this application part, that the solute, it may be synthetic, these are the molecular weight. If it is less than 2000 or greater than 2000. For less than 2000, we have the ionic, ionizable, non-ionizable. Under ionizable, we ionized form, non-ionized form, and accordingly we have the different chromatography techniques. Then if greater than 2000 is synthetic, polymer or biopolymer. Then size exclusion, differs, hydrophobic. Then accordingly your classification goes on. Then we have the type of application in pharmaceutical, the mixture like antibiotic, sedatives, steroids, analgesics can be analyzed through this SPLC. Biochemical, we have amino acids, protein, carbohydrates, lipids can be analyzed. Food product, industrial chemical, chemical, polymer, forensic, pollutant, quality control. So all these fields, SPLC is widely used. Polyaromatic hydrocarbons like naphthalene, anthracene, this can be analyzed here to between naphthalene, chlorine, phenolphthalein, anthracene, pyrene, these are all your polyaromatic. Then isomeric compounds, where your two compounds are isomers of each other, that may be syn isomer or anti-isomer. So this can be separated. So sugar in polymer drinks. Then we have the size exclusion also for the sucrose in canned fruit juice, drug abuse, separation of nucleic acids like cytosine, adenine, guanine, and uracil, cytosine, which is present in DNA and RNA. This can be easily identified. Then analysis of amino acid in complex mixture, partition chromatography. This is your bonded phase chromatography or reverse phase depending on the polarity. And we have the ion chromatography where different ions gets identified with SPLC. And we have the this is tetra valent bond is there, R4N plus. And we have the medicines like riboflavin, thiamine, uh, pyridoxine, niacinamide. So all these ionic and non-ionic compound mixtures can be identified. Then again the chiral separation of enantiomers, where E and L, D and L forms of a specific chiral compound or chiral center is also identified. Then ion exclusion chromatography, where different ion is excluded, and we have the speciation studies. Under this, then we have the interfering HPLC with mass spectrometry. This is your HPLC, that is GCMS, which is used in the spacecrafts, and LCMS, HPLC. These are all advanced tools which are used in used as advanced separation techniques to separate different components present in a mixture. Then go through all these interfaces, moving bed interface, the electrospray interface, and all these things are there in SPLC. So try to remember the uh, instrumentation as well as the working and the different parts that are present in high performance liquid chromatography. What is the advantages and how it is separated from your gas chromatography. So for today's class, the tier 2 minutes are covered up, and now the session is open. 5 or 10 minutes is there to discuss different questions. If anyone having any question or anything to share or anything related to your program you are trying to know, you may ask or you may share any information. So it is on you students.
सर ये पीपीटी शेयर कर सकते हो आप?
हाँ कर दो, आपका कुछ है क्या ये वाला कुछ पीजीपीएससी का ग्रुप किए हैं आप, व्हाट्सएप ग्रुप?
हाँ, व्हाट्सएप ग्रुप ज्वाइन किए हम।
तो उसमें मैं यहाँ पे मेरा नंबर दे रहा हूँ, आप उसमें मेरा नंबर ऐड कर दीजिएगा, तो इट विल बी हेल्पफुल टू ऑल दी स्टूडेंट्स हैं। So this is my number. Just add my number to your WhatsApp group, and in that group I will share the
तो सर ये इनके प्रैक्टिकल कब होंगे?
प्रैक्टिकल का कुछ मैसेज तो अभी आया नहीं, अगर आता है तो आपके मेल में डायरेक्ट कम्युनिकेशन जाएगा, ठीक है?
और जैसे मैंने सेंटर दिल्ली भरा था,
तो
लेकिन
अच्छा,
क्लास तो ये, हाँ क्लास भुवनेश्वर लग रही, तो प्रैक्टिकल दिल्ली होगा फिर भुवनेश्वर होगा?
नहीं अब शायद आपका भुवनेश्वर ही होगा।
तो भुवनेश्वर तो बहुत दूर पड़ जाएगा।
हाँ, तो भुवनेश्वर भुवनेश्वर तो आपको मतलब शायद वो आपका सारा प्रैक्टिकल एक दिन में हो जाएगा, तो आपको 1 डे के लिए शायद आना पड़ेगा।
तो सर इसका जो प्रैक्टिकल बुक ऑनलाइन पीडीएफ भेज रहा हूँ, इसकी इग्नू
क्या
की
बोले?
साइट पे स्टडी मटेरियल था जो इग्नू की साइट पे,
हाँ,
तो उसमें ये MCH-02 की प्रैक्टिकल की नोट पीडीएफ नहीं थी उसमें।
ओके। तो आपका जो भी प्रैक्टिकल का MCH-L02,
हाँ
उसका पीडीएफ MCH-1 का मिल गया, MCH-L01?
हाँ, 01 का मिल गया, 3 का मिल गया, 4 का मिल गया, उसकी पीडीएफ मिल गई उसकी।
अच्छा, 2 का नहीं है?
2 का नहीं था उसमें।
तो ठीक है, ठीक है, ठीक है, हम कल आपको बताएंगे, ठीक है? हम थोड़ा देख रहे
हाँ
हैं,
जो आपके,
अगर अवेलेबल रहता है तो हम वो जो ग्रुप है आपका जो है उसमें आप ऐड कर लेंगे,
जी
ठीक है? तो आप आराम से स्टडी करिए, दिस इज वेरी important separation technique or chemistry or chemical analysis is there, and tomorrow we will have the next unit, that is block 4 unit, on tomorrow there is no class, okay? I think आपका जो क्लास है नेक्स्ट है वो 4 तारीख को है, 4 और 5। So tomorrow and day after tomorrow, Saturday and Sunday, no class will be there, and your class will be on Monday and Tuesday, on 4th and 5th. And after completion of my class, then Dr. Jyoti Prakash Dhal will take your class on spectroscopic method, MCS-3, from 6 onwards to 13, and then Dr. Rajesh Kumar Sahu, basic analytical chemistry, from 14 onwards to 22. So this is how your schedule will carry on, and if no question is there, let's wind up the session. So thank you all for your patient sharing, and on behalf of IGNOR Regional Health Center Bhubaneswar, I mm, thank you for your patient sharing, and hopefully we will meet again on Monday, that is 4th of August. And till then, take care of yourself. Thank you.
थैंक यू सर।